about a war, okay? But then the First World War, which was called the Generals' War, or the Sixth Grade, where people just sat in trenches without nothing happening. And then the more recent wars, we talk about the Vietnam War, which we did, in 1967-68 class, we talked at length about Vietnam War in class that I just finished, and Kevin and I had taught. One of those called the Television War. The Korean War was the so-called Forgotten War. But they get to name the Second World War, which obviously you can call it as the just war, an absolutely legitimate war. Of, but at the same time, other word that could be given the Second World War would be called physicist war. And it really was a physicist war, because we just saw the movie Imitation Game, the radar about, the computer word, that my friend Bruce is talked about in Turing's, invention of radar, which defeated the Battle of Britain. And really, actually, the Manhattan Project was primarily the star of the shows were physicists, and that was, and obviously, and the unsung heroes, who were the engineers. Okay, so that, but somehow it never got to engineers, never get enough credit, because they're in the background. And actually, I think the soldiers were actually were made sure that they had basic understanding of classical physics. Obviously, they were not taught, but they had to at least know the trajectory or how to operate the equipment that was there. And so there was actually the name that was given to physicist war was appropriate type of thing, that they had to understand at least the laws of mechanics, so they don't, aim the gunners and other people knew some of the stuff that they were. But it was really highly technological war. Okay, now I think this is the slide that I borrowed from Bruce Govia, which is, just a basic slide, which is, I think all of you we've all taken enough classes, but just as a refresher. And I think as for the people from out of state, we will send out a PDF with slides and notes. So, that would just be a refresher. I think, it's like, and including some of the other, I've taken snippets of some of the videos that I'll play, but some of the entire videos are almost an hour long, so we don't want this video class, so I was just, and obviously we are recording the class, I think, and that's, and if you have any friend or somebody, you could just ask them to drop in type of thing. And so, because I don't think Ollie is going to go bankrupt if they, just drop in. Okay, so this is the outline of the class. This is, and just because this is the form that will, just as a refresher, I send out the guidelines, but well, at least we need to understand just basic of this for the non-science majors. I apologize that this may be the most rather heavy science class type of thing, but we need to understand how the word fission came about before we delve into the more interesting part of the history, which was the German and the British efforts for the atomic project, and then followed by the most massive and successful government project that was carried out, and costing at least several $billion, and was completed in record time. And the story behind and it's an interesting story as to how it was called to the Manhattan Project. And Trinity was the name of the test that was carried out in New Mexico, in Hiroshima, and the various spies as to how we ended up getting the secrets, the Russians. And I think if time permits, we'll dwell a little bit into the hydrogen bomb, because that itself is a separate class by itself. So this is the general agenda, but as if you know, as to how I'm a slob at heart, so I may not be able to stick entirely to it. I tried to go in a chronological way to make it a little bit more palatable. So now, just to show that I'm not just a science geek, but just at least I have a little bit of culture, we'll introduce the topic with the Greeks. The Democritus introduced the word atom. Atomos means unsplittable. Okay, so this was the start of things, and that was as far back as 416 before current era, and this was, this is the Democritus himself, and Now, this is in the great books class, we talked about Lucretius, and this was just to show that this was a book called The Swerve, which was about the uh, 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 lesser known philosopher named Lucretius, and his book that had disappeared from and was obscured for almost 1200 years and was rediscovered, in the Renaissance era, uh, by a clergyman named Poggio. And Stephen Greenblatt, who is a Shakespearean scholar, has written a book called The Swerve. And look, and the reason for mentioning Lucretius is this, because he was an Epicurean philosopher, and in a lot of his writings, he referred to Democritus and atom as underpinning of all the living things. And so, even that far back, their thinking was they were way ahead of their time. And even not to be outdone, Plato himself gave a geometric twist to all the objects because he gave all the basic elements fire, and because he was a big geometrian, so he gave, okay, it's one-dimensional, two-dimensional, three-dimensional, or four-dimensional type of thing. So fire, water, air, and ice. So, but he was a little bit off the track. And then after the false starts and other stuff, nothing much happened for several hundred years, and then we'll talk about when the atomic theory came into existence. Okay, and that starts after the age of the rise of the Industrial Revolution, and with the steam, it became necessary to figure out how to use the steam engines more efficiently, and that led to research in the science of thermodynamics and heat transfer. And until then, and even at that time, so I'll jump over one more slide to introduce. Now, but this is just, so you can't trust atoms, they make up everything. So this was just a cute cartoon just for this. And so nothing much happened for a long time until an English physicist, a polymath in true sense of the word, named John Dalton, and he worked on varieties of subjects, and these are so-called Dalton's laws, and he was one of the founders of chemistry as we've come to know it in present time. And these are some of the principles that, just to refresh what you might have studied in, middle school or high school chemistry. All matter is made of atoms are indivisible and indestructible, which obviously, that's all the class is all about. Right? And all the atoms are identical in mass and properties, and compounds are formed by combination of two or different atoms, and there's chemical arrangement. So there's other varieties of so-called Dalton's laws. And he was an unassuming Calvinistic chemist in Manchester, and he was and he was way ahead of his time, and he laid the foundation of chemistry as we've come to know it. Now, again, but this time, this was, even though he had proposed all these ideas and based on prior work of other scientists named Avogadro number, which we may remember the name from high school chemistry. But these ideas were not as easily accepted. And the people thought this was just a concept and something that you could not see, because science was visualizing with microscope and things. And since atoms were not visible, this idea was not as easily accepted. And there was, and just to refresh your memory, a guy named Planck, devised Planck's laws and was the founder of the science of thermodynamics. But again, that was hard to accept. And so much so that another well-known physicist named Boltzmann, actually, his ideas were chastised so much so that he was also suffered from depression so much so that he actually committed suicide, only to be proven that at the same time his ideas were actually confirmed by a guy, a physicist, whose name is synonymous with the giants of 20th century, and his name is Albert Einstein. Now, just to show it and I'm sure some of you can come up with the answer. What was Einstein's Nobel Prize given for? Okay, it wasn't given for relativity. it was given for photoelectric effect. And prior to that, Einstein had written a paper on Brownian motion. Okay, and Robert Brown was a 19th century chemist from Scotland, and he had written about the movement of pollen particles in water as to why they jiggle. Okay, and nobody, people just thought about it's kind of a crazy idea. Who wants to bother about that? But Einstein, based on mathematical things, he had proven that the pollen particles jiggle because it was Einstein's contribution and obviously he figures heavily into our subject matter. So we introduced John Dalton, and this was the famous John Dalton's picture who shows up. And now, the second thing that gave start to that comes with the accidental discovery of radioactivity by a French chemist named Henri Becquerel, and this was in the around 1896, and he was working with various ores and chemicals, and he exposed a chemical named potassium red uranyl sulfate to sunlight, and was placed on a photographic plate wrapped in black paper, believing that uranium absorbed sun's energy and emitted X-rays. And this hypothesis was disproved due to a cloudy day overcast in Paris. And for some reason, he decided to go ahead and develop the photographic plates anyway. And to his surprise, that the images were strong and clear, proving that it wasn't the sun after all, it was uranium that was emitting the radiation without any external source of energy. So this was the start of radioactivity, and that laid the foundation of the atomic science as we come to know it. And later on, we know the well-known scientists, the Curies, who extracted various radioactive elements, and these are well known as radium, and the other element that she discovered is polonium, and named after her home country of Poland. So this was one of the beginnings of now, and this was Henri Becquerel, and along with the Curies, and this was his famous photograph of the radioactivity that he took. Now, then obviously this is not, and at the same time, other things were happening. There were three things just happened, as it happens so often in science, that they happen at the same time. And prior to that, I think I did a class on history of cardiology and advances, and this was the famous, in 1895, a German physicist named Röntgen had discovered mysterious X-rays, and while he was working with a cathode ray tube, and this was the famous photograph that he took of his wife's hand, which shows her ring, and frightening the daylights out of her, that she was so shocked I've seen my own death. And then again, these two inventions, radioactivity and X-ray, became immensely popular. At that I think we did a history of science class this summer, and we talked at length about it as to how people were going. And some of you may remember as to how X-rays were used to measure that whether your shoes are fitting or not. And the radium became tremendously crazy, so much so that people were putting radium in all sorts of things, including radium toothpaste and makeups, and so it just became a craze until, and the infamous case of painting of your wristwatch dials, when people the ladies were putting the brush in their mouth and to get they got radiation, and so there was the infamous the danger of radioactivities where people were not aware. Now, at the same time,
to demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube which has a metal cathode, metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
So this was the introduction to the famous discovery of electrons. And this was done by the giant of who founded the atomic physics and got the head start, well-known man, a scientist in Britain named J.J. Thomson. And he named these particles as corpuscles. And subsequently, the name was given as electrons. And he along with Röntgen, were some of the earliest Nobel winners. Röntgen got one of the first Nobel Prizes for discovery of X-ray, and J.J. Thomson was the Nobel recipient for physics in 1906. And one of the earliest Americans who got the Nobel was to measure the charge, electrical charge of the electron, was a guy named Robert Millikan. And this time the UK or Britain was the hard place for scientific discoveries in physics, and a well-known place that some of you may have heard about, or I would imagine most of you, is a place called Cavendish Lab that was named after older physicist Lord Cavendish in Cambridge, and they have been. And about as many as 30 Nobel winners have come out of Cavendish Lab in various disciplines, not just physics, chemistry, but including the most recent one, the ones such as Crick and Watson in biology. So they've been at the forefront of research in all the three major disciplines. So these three discoveries, came to. Now, why did we mention X-rays in here? Because obviously X-rays are electromagnetic waves, as you remember from the spectrum, of like ultraviolet, infrared, X-ray, based on the wavelength. Because all the X-rays have been used widely to study atoms, based on the science that our chemistry professor, Dr. Hasselkin, said, well, X-ray crystallography has been the big backbone for researching atomic science, along with various clever experiments that were done in the Cavendish Lab. And you saw as to how, from such a simple equipment, they were able to come up with the concept of electrons. And obviously, this work was based on the shoulders of other giants, such as Maxwell and Hertz. And there was the early days of electricity, and including not to, and mentioning on the other side of the Atlantic, work by Edison and Tesla. So the foundation was gradually upon the build of electromagnetism, and the three discoveries that we just mentioned, to repeat myself: discovery of electron, X-rays, and radioactivity. So they all came together to give rise to this science of atomic physics. And that brings us to the man who can be truly called the founder of nuclear physics, or atomic physics, as we call it, this is Ernest Rutherford. Okay, he was a New Zealander, and obviously grew up on a farm in New Zealand, and was brilliant and managed to win various scholarships. And it's from a middle class background, was able to win fellowships to Cambridge, and was interested in radioactivity, and started working on that, and made varieties of groundbreaking discoveries in physics, and including a model of atom. Because as I showed going back, and J.J. Thomson had proposed the model of atom, which is in the upper corner, called raisin pudding model, and Rutherford worked on it, and I'll have a nice small video of Rutherford's experiment about discovery of nucleus, and that was one of the most elegant experiments in physics, as you can see, as you'll see shortly. And he proposed the new model of atom that we've all come to recognize. And he also discovered the three types of radiation that all of us have learned in school: the alpha, beta, and gamma radiation. And so he worked on various fundamental concepts that have led to the foundation of atomic physics in the modern era. And so atoms exist in their complex structures, and we proved that radioactivity transmutes elements and can release great energy. And this was actually the dream dating back to Sir Isaac Newton of alchemy, that by bombarding various chemicals with radioactivity, they were able to do what has come to be known as transmutation of elements. And just by blasting various elements, they were able to convert nitrogen into oxygen. So that actually gave rise to finally the chemists were able to realize the dream of alchemy, of transmuting elements. And so then again, he also devised the concept of decay of various elements, including how much time it takes for half the amount of to be decayed, so the concept of half-life. But at the same time, he was so there was an experimentalist par excellence, and he obviously he mentored a large number of Nobel winners, and at the same time, and there's some famous statement that can be attributed to Sir Ernest Rutherford, that in science there is only physics, rest is stamp collection. I'm sure the chemists were not exactly thrilled to hear that, but surprisingly, his Nobel Prize was in chemistry. And he later on moved to McGill University, and then did work there, and went back to Cavendish Lab later on. So that's enough about, and these are the basic concepts of three types of radiation that later on it was proven that the so-called alpha radiation is a nucleus of helium, and it charges the amount of electricity and the mass, and these are all important factors. And the gamma radiation is an electromagnetic wave, while so-called beta radiation was later on proved to be just the electron, which is the negative charge. And how fast these isotopes travel, that is important when it comes to transmutation of the elements. And gamma rays can be dangerous, to exposure. So these are the various concepts that Sir Rutherford. And now, how did he prove about the discovery of nucleus? This was one of the famous experiments that I alluded to. There is no audio on this, but I'll explain this in just a second. Okay, now this may sound like a somewhat difficult concept for the non-science majors, but by this time, one of his well-known students named Hans Geiger, who was German, he had discovered something called the Geiger counter. So based on the strikes that took place on the back plate, they were able to count the number of particles that hit the plate in the background. Now, what he had assigned his students, the Geiger and Marston, to count the number of particles that traveled through from the source, that traveled through and hit the back gold foil. And they were doing that for a number of days, and they were counting. And this was, and at that time, so, and he was once, uh, and nothing much was happening. So Rutherford had either a hunch or article that, well, why don't you guys check on the same side as the alpha source is placed? And after waiting for days, they were able to count some particles on the same side as the alpha particle source was. And this proved that the alpha particles, which, which were released from the radioactive source, were bouncing back, were hitting something in the center of the element and were bouncing back. And that was almost like, so atom is generally an empty place, but they were hitting straight on, were hitting the nucleus. A small percentage were detected at a large angle and were backscattered. And because they were large and have a mass of about 8,000 times of mass of the electron impacted the foil at high velocity, a strong force was necessary to create the backscatter. So this has to do with like something that hit the straight on and bounced back. And that proposed the idea of the nucleus. There was something in the middle of the atom, and that was the idea of the nucleus. And that gave rise to the structure of atom as we have come to know it, because the electrons that are fairly lightweight and are orbiting around the center heavy nucleus, and which was made with positive difference. Now, okay, and so this was, so the earlier model, the so-called plum pudding model of the atom, was discarded, and this was the Rutherford's model, as you can see in the picture on the side. So this was one of the ideas. Now, for those of you who are more astute may realize that, okay, well, these are the positives and negatives as to why don't this electron collapse and fix into the center, because positive and negatives should not keep orbiting around. So that was a problem that they had to deal with. And it took almost several years to come up with the answer to this. And that story is coming up a little later. Okay, but this was one of the earliest, and Rutherford was, okay, so we have seen this experiment. Now at the same time, okay, and another totally antithesis of Rutherford was from a very humble background, was still from the colonies, was sort of looked down upon by the English establishment, but gradually was accepted by J.J. Thomson and rose to be after the Nobel winner, and is so glad. But at the same time, he had a student who came to study with J.J. Thomson, named Niels Bohr. He was from a very upper class Danish family, and he came to study with J.J. Thomson. And unfortunately, in those days, he managed to point out to an error in J.J. Thomson's book, and obviously that did not go well. So he finally gave up on working with J.J. Thomson and started working with Rutherford, and they hit it off quite well. And he tried to come up with the idea as to why the electrons don't jump, okay, or don't fall down. And he came up with the idea that the electrons are almost like in a high-rise building. They're staying at various levels. And he proposed the idea that there are various orbits, and electrons need to change the orbit type of things, and and that is the start of so-called quantum leap. Now, this was a theoretical concept at that time, and it was hard to explain. And there's a big story about how this gave rise to the model of atom and the rise of quantum theory. Okay, and again, Niels Bohr, and then he was received financing from the beer company in Denmark, and who built up a big Niels Bohr Institute. And he wrote varieties of paper on the trying to explain the atomic model, so-called Bohr's model. That and this is, and I think I don't know, maybe John Hassel can explain it better than I can, perhaps, but I'll give it a go. I think that these are the various energy levels in hydrogen, and the electron releases amount of energy, which is discovered released as photon, and and so this was a way to explain the whole periodic table as we have come to know it. But it took not just Niels Bohr's work, but other people's work, which we'll get to in just a minute. Now, the other things that I've introduced, are, we'll get to that later as to what are some of the meetings that took place in 1927 as to explain the whole idea of quantum physics, or quantum mechanics, as we used to call it in the old days. And Niels Bohr figures large in the history of atomic physics, as we'll talk about towards the end of this talk, or perhaps in the early next week, when we talk about how the whole idea of atomic breaking the atom came around, and how the idea traveled with Niels Bohr from to the other side of the Atlantic. And that's a fascinating story that at least the history buffs will enjoy. And some of the statements that we talked about, that one of the statements with Rutherford, that anyone who can say we can utilize atomic energy is talking moonshine. Okay, so he was, even though he had done the pioneer work on transmitting element, he was rather skeptical about the whole idea. At the same time, Niels Bohr is credited to have made a statement: you need to turn the country into a factory for an A bomb. Little did he realize that the United States did exactly just that a few years later. So that's good, and then again, this is one of his famous quotes about quantum physics. If anybody who has been profoundly shocked, you haven't understood. And this is similar stories goes about Einstein's general theory of relativity. As to when he was sitting at a table with the famous astronomer, okay, and said, okay, well, there are only three people who understand general theory of relativity. And the scientist had a puzzled look, said, yeah, there's you and me. I'm trying to figure out who was the third one. And so, okay, and so this is, the concept of the Bohr model of negatively charged electrons orbit in orbits. Electrons keep a certain distance from the nucleus. They gain energy as they move up and down, and by releasing energy. And this is based on so-called Planck's equation. I mean, if you don't remember all the numbers and other stuff, don't worry about it. But this is the amount of energy that is released based on H is called Planck's constant and velocity. Okay. So this is just, and this is one of the ways that finally chemistry becomes physical. So it was the marriage of physics and chemistry that took place. Okay. All right, I think, and Niels Bohr, actually had a big team working with him at the famous Bohr Institute. Along with that, and when he received the Nobel Prize at that time, and based, as I mentioned earlier, that based on the electron orbit, they had tried to make some sense out of the periodic table, which was proposed by the giant Russian Dmitry Mendeleev, right? And it just by serendipity, when Bohr was receiving his Nobel Prize, and based on electron orbit, they had predicted, yes, that there should be a missing element, because as you may or may not recall, Mendeleev's periodic table has some gaps in his periodic table. They had proposed that there should be an element at this particular place. And now this just blows my mind as to how he labeled some of these names based on Sanskrit, okay, which is the classical Indian language. Okay, and he had named the missing elements is eka aluminum. Eka means one in Sanskrit. And, and he had named another missing element called Dwi, manganese. Dwi means two. And so there were certain gaps in the entire periodic table that Mendeleev had worked out. And by surreptitiously, when Bohr was accepting his Nobel Prize the night before, he received a cable from his laboratories in Copenhagen that we have discovered the new element hafnium based on the entire prediction. So this was, and hafnium was the old name for Hefner for Copenhagen. So that was named after him. So it just showed as to how theory and practice came together, because based on, so the research was done just at the same time. And again, similarly, they had predicted that the various properties of various missing elements, for example, that element 72 will be like zirconium, not a rare earth. So it was almost like predicting alchemy or true nature. So it was an amazing amount of discovery that put the physics and the chemistry all together. And at the same time, so this idea of quantum physics, which was hard to accept for the traditionalists. And a big fight took over in the physics community between the traditionalists and the new generation of physicists, starting with Niels Bohr and his prodigy, who will figure large into the history of atomic science. And again, after this, the particle physics has gone absolutely crazy. And obviously we're not here to talk about particle physics, but these are the varieties of particles that have been discovered, not just the three basics ones that we all are familiar with, electron, proton, and neutron, but varieties of physical particles have been discovered. In fact, as recently as just within last 1 month, 12 new particles have been discovered by the CERN laboratory. And these are the varieties of combination of so-called quarks that are there. But again, we are digressing, so I shan't dwell too much on it. Please stop me at any time if I'm going too fast, because it's my fault. I generally talk too fast. I know, but so please stop me at any time if anybody has any comments or questions. Okay. Now, one of the well-known persons who will figure large into our discussion or our class, especially when it comes to the German atomic effort, is this man, Werner Heisenberg. And obviously, if you are television fans, you may have heard about, I haven't seen the show, but there was a TV show on one of the cable channels called Breaking Bad. And the lead character in that was named Heisenberg. And obviously no relation, but this was one of the, he was a brilliant German who was a student of Niels Bohr. And he worked initially with Niels Bohr on solidifying the quantum physics with something called the uncertainty principle. Okay? That the position and the momentum in the charge cannot be absolutely known. And while trying to measure, we are disturbing one of the two. So that's called the Heisenberg uncertainty. And that was very hard for the traditionalists who accepted the deterministic principle. So there was a big fight that took place in the physics community in primarily in Western Europe at that time, because at that time, you should read me fine. America was a little bit in the backwaters of the physics community, as we'll talk about earlier, but they caught up very rapidly. And again, I hate to use the word loosely with polymath, but Heisenberg was not just, it was a classical pianist, a chess player, a brilliant mathematician, and just to work on the quantum principle, he actually devised a whole new concept for mathematics, or algebra, which is called matrix math or matrix algebra, because and that helped solidify the principle. And that was a huge controversy that went on between the classicists in that camp, where Albert Einstein and a guy that you may have heard about very well called Schrodinger, which was called Schrodinger's cat, and which is the famous Schrodinger's experiment. It's well known to physics students all over the world. And on the other camp, the quantum, the new group pioneered by Niels Bohr and Heisenberg. And that argument just went on for almost 20 years, one should say, until 1927. And the reason why I'm referring that this was a famous Belgian chemist named Solvay had an industrialist chemist named Solvay had financed various physics conferences starting from the early 20th century. And this was the famous conference that took place in 1927, the Solvay conference, the fifth conference. And as you can see, this is like the who's who of physics community, starting from the center figure that you'll come to recognize, Albert Einstein, right here. And varieties of other giants, Erwin Schrodinger, okay, of the Schrodinger equation, and then only woman who's in the picture is Marie Curie, who is in the setting third from the left, and Max Planck, who is next to her, who is the famous Planck's equation person. Albert Einstein we talked about. Okay. And on the back side, there are other well-known scientists. Erwin Schrodinger is the gentleman with the bow tie right in the third row, and Werner Heisenberg. So these are the, and he was only in his early 20s, and Wolfgang Pauli. So these are all the famous figures and out of this, and there were like about 30 people, out of which 19 went on to be Nobel laureates. Okay, and now, at the same time, Bohr's concepts of quantum jumps were theoretical. And another brilliant Englishman, helped establish this. Okay, let's play this so how he went on to work on by this time, a person in the UK had discovered something called the spectrometer, which is to measure the wave. Okay, so this is, this gives more science. And the reason why this is important, because when it comes to the atomic number, and when we talk about the so-called yellow cake, which is, by the way, that was a clue yesterday on Jeopardy. Yellow cake is referred to as uranium, and which is the element that we'll be talking about at length, in our history of atomic science, atomic age. And so this was an important number of the atomic number in so-called, and this gives us to the fundamental concept of so-called isotopes, because the same element can exist in different forms. For example, carbon-12, it has 6 and 6, which is the more common amount of carbon, while carbon-14, which is used for dating the age of carbon in nature, and which is the foundation of archaeology as we have come to know it. And so this is a very important concept when we'll talk about uranium, because uranium-235 has 92 protons and 143 non-charged neutrons, and which is, uncommon in nature. It's only 0.72% of naturally occurring uranium is uranium-235. And that is very important to the creation of that requires various processing. And that's one of the reasons for getting into, the so-called more abundant uranium is uranium-238, which has 92 protons and 146 neutrons, which are much more abundant. So this is an important element and concept to get across. And so, and I'm sure a lot of you have heard that, and this is, and so the amount of, so, all right. And this is the basic concept of hydrogen, which we may or may not get into. Is hydrogen, and so-called, it comes in two different forms. That deuterium is the hydrogen proton combined with the most basic element, most abundant in nature, hydrogen, a proton and neutron, the so-called heavy hydrogen. And that again, will figure largely in our talk, because we'll be talking about heavy water, which is used to slow down the reactions, and figures widely into the German effort to make atomic bomb. Okay, we're coming up to 11 o'clock, so if everybody's interested in taking a 5-minute break, I think it will not be unreasonable to take a few minute break and come back at 11:05, perhaps. 12:05, so we should just push right. I mean 11:05, so I think I'm still I have to. Okay, so I think we'll get started. Everybody will be. I think I've lost everybody's windows now, so I'll jump right along. People will filter in as we go along. Now it is interesting that how elements go back together. And so when elements change, it's important to mention so-called mass energy equation type of thing, that the mass of the nucleus is less than that of the component. So there is energy that is required to break it apart, and it's so-called binding energy. This is an important concept when we talk about heavy water and breaking down. Now, somewhere along the line, this element is binding energy of the nucleon. When we combine the proton and the nucleus that are in the center, there is something called the binding energy. And this is a very important concept, because all the elements actually, now somehow iron is very stable element. That's why it's one of the most abundant elements. It's very stable. And as you can see, that based on this, hydrogen and helium want to be more stable, while the uranium element is unstable type of thing. So that somewhere along the line, at the level of iron, the properties of the elements change based on the amount of energy that is released versus energy that is required to bind. So this is, and this is the similar curve that is, so this based on to the concept as to when the elements break down, this is where the famous equation comes into picture. So when the heavier elements are broken down, they release the energy when they break down into the lower elements. And so this is the basic fundamental principle that governs all the atomic reactors and the atomic bombs, and the binding energy of that. So the properties of the heavier elements beyond iron is different as opposed to the lower elements. So this is the curve, and this is the same curve as that the astronomers discovered into the abundance in the universe, right? And again, we talked about, yes, that the concept of neutron took a long time to discover, and it took one of Rutherford's students named James Chadwick, who studied with Hans Geiger that we talked about, and he's credited to have discovered the neutron. And the third type of subatomic particles, which has neither a positive nor a negative charge, okay? And the atoms of the same elements differ in the number of neutrons, leading to the formation of isotopes. And this took until 1930s to prove. And this is an interesting story that the various famous people, including the Curies, missed the discovery of neutron. So this is, again, the similar experiment that we can see from this little cartoon here. That polonium is a radioactive source that is releases out a particle, and as the particles pass through paraffin, and these are slowed down, and and emitting non-ionizing radiation. I'm sorry, click that. Non-ionizing radiation, and so this was some of the concept that the Curies totally missed this concept, but and this was proposed at the Solvay conference in 1930s, and James Chadwick established the discovery of neutrons, which are again very important in the splitting of uranium and the atomic bombs. Now, another person that is equally important when it comes to the neutron discovery is to those of you who are in the Midwest recognize, the big Fermi lab near Chicago that is named after the famous Italian scientist who was a well-known experimenter, physicist, as well as theoretician. And his the famous experiment in Chicago, which we'll talk about in, I think early next week. And his and he is credited to have, now instead of using alpha particle source, as we talked about when the earlier scientists used, he used neutron source. And the neutron source that he used is radium and radon. This is radon 222 and radium, along with covered in this simple tube is covered with beryllium, which is one of the metals. And with this, they systematically started bombarding various elements entire through the periodic table. And he had a team of various scientists that worked with him in Italy. And this is where he was working on so-called neutrons and trying to systematically arrange, go through all the elements of the periodic table. Now, interestingly, they found out that while they were doing experiments, the amount of neutrons they were discovering on the screen were a lot more if they worked on a regular marble table versus a table made of wood. Okay, and this was bizarre because they couldn't figure out why the table that they worked with made a difference. Okay, and apparently Enrico Fermi had a brilliant hunch that perhaps the table is made of softer materials and the neutrons were bouncing back from the softer table and we're slowing it down. That's why we were getting the more count of neutrons on the other side. So it's interesting. So that came up with the concept of so-called fast neutrons were bouncing back like throwing billiard balls on a solid surface. They were bouncing right back and going through, while the wooden table was soft, was slowing down the neutrons, and that's why you were getting more counts on the other side. So there was an interesting concept of so-called fast and slow neutrons. And again, why am I harping on that? Because that's an important concept when we talk about splitting of the uranium as to fast versus slow neutrons. I think, and that has got to do with the so-called, they had to put material which would slow down the transfer of the neutrons because if you want to create the bomb, you just can't have neutrons all flying all over around, because then they would not, start what is called chain reaction. And so that is why the slowing down of neutrons was an extremely important matter. And so this is, so the Enrico Fermi, I guess, the credit for discovery of and he saw that the various elements were transforming into different, and he's credited to have discovered so-called trans-uranium elements. And that was his Nobel Prize in 1938. Now, again, as you can see, if you remember your history, in 1933, the Nazis took over. And that was one of the reasons why Enrico Fermi, when he received the Nobel, he had requested the Mussolini government, it would be nice if I can travel with my family because it's a big honor for the Italian, for Italy. And so they were allowed to go, and instead of returning to Italy, they immigrated to Colombia in the beginning and later on to Chicago. That leads to the famous work that was done in Chicago at the Fermi Lab. And I would have a lot more to say afterwards about it. Okay, let's see if we can play this.
Fine, Bueller.
Okay, so this was, that gives you an idea as to how, so it brings us to the main crux. So that's one of the reasons for going through all of this, Now, this is the story of the Exodus. This has nothing to do with the biblical Exodus, but the Exodus to this. Okay, now this is always, as somebody growing up in India, this was always a bone of contention for all Indians because the swastika was literally hijacked by the Nazis and maligned in the all over world. Because in a lot of cultures, and this is for those of you who are interested, this is a link that's there, but was used all over the world as a religious symbol, and including in the Americas also, in some of the Native American cultures it was used. So the swastika has been, and the reason for mentioning this was the big exodus that took place. The names in physics who were had to leave Germany looks like who is who. Hans Bethe, Max Born, obviously Albert Einstein, Otto Frisch, Lisa Meitner, Schrödinger, Leo Szilard, Edward Teller, who was the so-called founder or father of hydrogen. These were all, prior to 1933, there were Germans had the monopoly in terms of Nobel laureates, and later on, they were way behind that. And so this, and the reason for this exodus was obviously very obvious because they were, being blackballed and they lost their university jobs, and a lot of them lost their families. And this was one of the things that one of the physicists that we'll talk about a little later on, he went to one of the economists at one of the famous universities. Well, says, well, what's going to happen with all the Jewish professors and scientists? Okay, well, it was a rather cynical statement. Well, that the French will pray for the victim, the Brits would organize the rescue, while the Americans will pay for them. Okay, and that is exactly what happened, basically, because quite a large number of the exiled scientists settled in Britain, and another large portion came to America. At the same time, the French were obviously they were in their own trouble, so they were not able to do this. And again, and this was again, as I mentioned earlier, the United States was somewhat in the backwater in the first of the end. There was a huge influx of physicists. There was a huge rise in the number of physicists in the United States between 1919 and 1932. And interestingly, at that time, psychology was becoming the native science. So they did a very psychological profile of various physicists. That a lot of the physicists were usually from the Pacific Northwest or Midwest. They were the firstborn sons of professionals, usually engineers and professors type of person, people who were generally loners or with high IQ. Not too many of people were from the New England, because the New England somehow produced more lawyers than physicists. Okay, so this was one of the things after the high side. And so much so that this was, and then a lot of the physicists were in dire distress, so much so that one of the other well-known physicists that we'll talk about in just a few minutes, and he even thought about migrating to British India because that was some desperate times, And now, moving on to the other side of, two well-known Americans who were figures, so this is, these are the two well-known cowboys who you may or may not recognize are, Robert Oppenheimer and Ernest Lawrence, okay? And they were two good friends and they were total antithesis of each other. That Oppenheimer was a rich Jewish person who was a classicist European, was truly well versed in various languages, literature, and very experimental, were theoretical physicists. While Ernest Lawrence was a hard-charging Midwesterner who grew up in North Dakota, and what had famously ambitious. And these two people managed to get together in the early 30s at UC Berkeley. And obviously, Oppenheimer had studied at Harvard and later on at Cavendish laboratories and various laboratories in Europe. And did a lot of work earlier on black holes and had worked on varieties of fields, so much so that he was so that one of the reasons why he didn't qualify for a Nobel Prize, but because he was truly able to cover a lot of fields, and later on was the head of Los Alamos, much to the chagrin of various other people. while Lawrence was an extremely practical person who worked on the cyclotrons on the West Coast. And we'll talk more about Lawrence. And again, so this was a good friendship that they were together. And at the same time, post-war, there was a little fracture that took place between the two. And we will talk about that after in the third or fourth class. And this is Ernest Lawrence, and this was one of the concepts that he had come up with, that he happened to be, he was ambitious and had a PhD in physics at Yale, and subsequently with his mentors, he was recruited because Berkeley was just establishing the physics department, so he was recruited on the West Coast. And at one time, he was reading an article about accelerating, electrons through magnetism. So he happened to read an article in a German magazine, and so based on that, using the same electrical potential and doubling the energy by switching from positive to negative in order to push these electrons, push and pull. So I'll have a nice little video about it in just a second. And this was one of the concepts of using magnets and electricity to accelerate electrons and to split to create more and more particles. And he became something called atom smasher, or later on, because it was circular, it was called cyclotron. And this was the rise of big science. And again, he knew bigger and bigger magnets weighing several tons. And he was a master at raising funds for financing some of this. And the reason why he was able to get this funding, because some of the isotopes that he created were used for medical purposes also, such as radioactive iodine and for cancer. So a lot of the people who had cancer in the families, a lot of the businessmen and industrialists, opened up their checkbooks. And that's one of the reasons why Lawrence was able to get huge amount of funding. And luckily for him, his brother was a physician. So those two brothers worked together and were able to get huge amount of funding of millions of dollars from the Rockefeller Foundation and various other industrialists. Okay, a well-known industrialist that we'll talk about later on in Alfred Loomis, who was a businessman, industrialist, and a financier, and a very physics lover. So he was able to get a huge amount of funding for these huge machines called cyclotrons and linear accelerator on the West Coast. And this is UC Berkeley, and we'll play this video.
Berkeley was the
So if you got the idea type of thing, and this is, so the rise of Berkeley, and this was one of the meetings that took place at the cyclotron after the projects for uranium were approved. The who is who of U.S. James Conant was the physicist. Vladimir Bush was the head of MIT and Harvard. The committee that Alfred Loomis was the businessman who I talked about earlier. And it's a fascinating book about the rise of big science that took place on Berkeley. And again, to use the cliche word coined in the Eisenhower era, the rise of the so-called military industrial complex that dated back to before the war. So we talked about, and Lawrence was again, was ferociously ambitious person that right from high school onward, he had this, I'm going to be famous. And right enough, he was. And the so-called radiation lab became a major player in processing uranium later on. And it was, and again, but at the same time, to his credit, he favored not just dropping the bomb, he favored demonstration to the Japanese. But that story has to wait. And he worked on science as well as medical isotopes, including cobalt-60, iodine-131, technetium-99. And these were kind of the workhorse of modern medicine as we've come to know it. And so, okay, so, but that's just for people who are real science history fans. And then we talked about how, and what happens is even scientists are not infallible. As the famous children of Marie Curie and Irene and Frederick Joliot Curie. And they had a lot of hit and miss. And when we talked about James Chadwick's experiment of discovering neutron, Irene and Frederick Joly missed the neutron discovery. But later on, now they made up for it by discovering so-called artificial radioactivity, where they converted aluminum into phosphorus. Again, basically so-called alchemy, as we talked about earlier. And so this was now this time, and there were, and this was one of the big, that was one of the things that they received the Nobel Prize for. So these are the famous physics family, and the daughter of Marie Curie, radiation pioneer. So I think we won't dwell too much into it. But now again, they also worked on converting the elements. So they worked on chain reaction, and by this time, people were sure aware that this could have potential military sequences. So they were told to keep this paper secret. And again, so this was, and we talked about how Enrico Fermi had this so-called chain reaction. And this was one of the things that how, again, this is, to me, this was mind-blowing as to how, okay, well, the reason why I included this Italian statement as to, and people would ask Fermi as to how did he come up with this idea? His answer was in Italian, on intuitive, formidable intuition. And so that was one of his, shrugged shoulders reply. Now, at the same time, that now, as we mentioned earlier, and in the little video clip that I showed, that he had missed the looking for the lower weight elements when he bombarded uranium with neutrons. And again, a lady who gets less credit was a German chemist who had proposed that they should be looking for lower atomic weight elements. Her name was Ida Noddack. And she had proposed this as far back as 1934, that people were missing the boat when they were looking for only the next element in atomic weight when they were bombarding uranium and other heavy elements. And she had proposed that in an article. But again, so her suggestion was, it is conceivable that the nucleus breaks up into several large fragments, which would of course, the isotopes of non-element would not be neighbors exactly in the same distance. But her idea was never taken seriously. And one can hypothetically visualize that she was a German chemist, and if the Germans had taken her idea seriously and had started working on fission or working on uranium atoms a lot more seriously at that time, the history of the world would have been dramatically different. Her ideas were never taken seriously, neither by the Germans nor by the physics community at large. So that's a little element of history as to so-called what if that one can. We talked about the exodus. I'm sorry, this is a slide. And at the same time, there was this huge exodus took place from Hungary. At that time, Hungary was, hotbed of geniuses. And these are obviously, a lot of people will not recognize these pictures, but once I say names, they will come to one of the persons from starting, John von Neumann, who is a famous polymath mathematician and the founder of computer sciences. The second is a well-known mathematician who was an eccentric mathematician named Paul Erdős. So much so that sometimes I've read the history of mathematics, and mathematics is called Erdős number, and how closely you are related to Erdős as to how all mathematicians, based upon who their PhD mentor was, based on that, it's called Erdős number. It's almost like, in the popular culture, there is something called the 6 degrees of Kevin Bacon. Okay, I think, your children or grandchildren may know more about relationship to Kevin Bacon in the movie industry. The same way in mathematics, something called Erdős number as to how far you're related to eccentric nomadic mathematician. He was one of the most prominent mathematicians in the history. And now mathematicians usually peter out by the time they are 30s, but Erdős would remain productive until in his late 60s. And he wasn't averse to taking amphetamines to improve his thinking. The next person was Eugene Wenger, who was a Nobel laureate in physics for his contribution to atomic nucleus theory. The last person, the one here, will feature prominently in our talk is this guy, Lawrence Zillard. And I'll get to him and the last but not the least is Edward Teller is in the left-hand corner. He was the so-called father of the hydrogen bomb. And he became sort of persona non grata because of some of the evidence that he gave in the Oppenheimer witch hunt that took place. That's the right word for it during the McCarthy era. And so these were well known. And this is a Medium, is an online computer magazine, and which we said. So, and the Hungarians were so genius that this was the sort of aliens in tongue in cheek. It was called the Martians of Budapest. Okay, so this was, they were all eccentric, and they were all immigrants from Hungary. So there were there were only two types of people, the aliens and the Hungarians. So they were the Martians of Budapest. Okay, now this is just, I just thought this would be interesting to see. And the recent economist had the article as to who will go nuclear next, whether it will be the Iranians or Saudi Arabians, as to, and this was from one of the British comedy writers. Why do the Iranians want the bomb? The Israelis have it. Why do they want it? They live in a bad neighborhood. Why did the Brits want it? They lost the empire. Why did the French want it? Because the Brits had it. Okay. Why did the Pakistanis want it? Because the Indians had it. Why did the Indians want it? Because the Chinese had it. Why did the Chinese want it? The Russians had it. Why did the Russians have it? The Americans had it, and they used it. It all started with a nervous Hungarian crossing the street in London, had an idea. His name was Leo Szilard. It started with an idea. Okay. And this is the famous street, if you're familiar with London, the Russell Square, near the British Museum and the library. Okay. And this was where he was crossing the street. And, he was as I mentioned earlier, he was the Hungarian exile. And he had read the famous book by H.G. Wells, who was published in 1914. Okay, The Word Set Free. In H.G. Wells, the science fiction story, he had written about the splitting of atoms and the word set free and the atomic bombs that were brought from the plane causing devastating effects. And the story continued with a French aviator on a bombing mission to Berlin. And the uranium bomb grenade was dropped. And so based on this idea that Szilard had read this book and he had just, and based on some of the research of the theories that he had read about, he came up with the idea that based on bombarding the atom, if one neutron can raise two, and the two can raise to 4 and 8, and so in geometrical progression, we can raise and sustain chain reaction and release energy. So based on this, he came up with the idea that a chain reaction can be sustained. This was as early as 1934. So much so. Okay, so this is about the Hungarian. So we talked about it was visionary. So much so that he took out a patent in Britain as early as 1934, before the chain reaction was practical. So this was the patent that he applied for. And he was paranoid about the rise of Nazism, so much so that he said, well, okay, I will take out the patent, but I want to keep it secret and not release it. Okay. So, and based on that, and he had also read the article by Lord Rutherford that it certainly is possible to, had written an article, there was little possibility of using nuclear energy for practical purposes, type of thing. So, but again, the ideas were, involving the scientific community that, so this was the patent that he had taken out. And again, obviously at that time, there was a tradition not to monetize the discoveries. So he had given the patent for okay, well, he did not want to monetize the equipment, but we're just worried that if this idea of chain reaction falls into wrong hands, it could have a devastating consequence. And again, so this is the famous Solvay conference, another picture that took place in 1933 about the structure and properties of atomic nucleus. And this is the first time an American was invited, Ernest Lawrence, who we talked about earlier with the cyclotron, and he's in one of these pictures. Okay, and so again, we've talked enough about the well-known who is who, so I think we'll move right along to the next one. To the right one. Okay. Now, this is where we talk about. This is the Germans had Germany had strong chemical industry as well known, in the early 20th century, and where they started with the industrial production of chemical dyes and the rise of various German chemical industries, IG Farben in Bayer, and a well-known chemist, experimental chemist who served in the First World War, named Otto Hahn. And he was working on, now he didn't believe some of the stuff that the Curies had done, and as usual, the national rivalries continued because the Germans didn't trust the French didn't trust the Germans, and the Brits didn't trust anybody. Okay, so that just continued, and he was a pioneer in radiochemistry, and he worked at the famous Kaiser Wilhelm Institute in Berlin, along with a well-known physicist that we'll talk to in just a minute. Okay, and he was working on the uranium atoms, and he discovered the results now based on the spectrography, which didn't make sense to him. Okay, and these were some of the experiments. Again, you can see that the experiments, the equipment was rather small, and for splitting the uranium and the research that was carried out. It was almost like a garage type of research as opposed to Lawrence's research that we talked about, which was on a mega scale. Okay, and so this was the two radiochemists, and Otto Hahn was a chemist, and he was not a physicist, and he worked with Lisa Meitner, who had a PhD in physics and was a professor in Berlin before the rise of Nazis. And again, with the coming in of Nazis, he had to leave Germany with the help of some of the Dutch scientists. And Otto Hahn was not able to figure out the results that he got. So he had written a letter to Lisa Meitner, and who was by that time in Stockholm. And this is the famous Lisa Meitner. And she, along with her nephew, who was a physicist, managed to figure out that the amount of the mass that had decreased when they split the uranium and some of the spectra that they discovered were the lower elements, which fit the characteristics of barium, which was way down on the periodic table. And obviously, this was early 1930s, and Einstein's paper was a few years back, as you can see from the cartoon. That was the famous, not E equals ma squared, but E equals mc squared. So she and her nephew put this two together in the role of fission, and so. And this is the famous Lisa Meitner, in her younger days and the older, and she and her nephew, they were both Jewish, and they figured out that this was what Hahn had done, was to actually split the uranium into a much lower element, and he hadn't realized that, but obviously with information and going back and forth between the letters, and they were able to figure it out. And Lisa Meitner and Otto Frisch wrote a paper, and that was published in Nature at the same time, that the fission of heavy element has been carried out successfully in Germany. And that paper, obviously, at that time, the scientific community relied on published work, obviously, much before internet, and the information became widely dispersed to the grand man by that time in Copenhagen, Niels Bohr, and obviously the information actually traveled across to America also. Now, Lisa Meitner was a very tragic story. She was, again, like the Nobel Committee, she was nominated for several times, but never got the nod. And this was the famous picture that I took from one of the videos about Lisa Meitner and Otto Frisch were out for a walk, and they were trying to decipher what actually Hans had done, Otto Hahn had done. And based on between the combination between the nephew and the aunt, they managed to figure out that this is actually what had taken place. They did the calculation about the amount of electron energy that was released from splitting the uranium, and based on, it was a huge amount of electron, 20 million tons of electron volt that was released from the amount of uranium that was split. And they said the calculations that they carried out actually absolutely fit with the Einstein formula. And that led to the famous paper in January that they released. And that wrecked this history. And this was our famous nephew, Otto Frisch, who by that time had migrated from Germany to Copenhagen to Britain. And now it's interesting how the name fission came about, because obviously they've done this word splitting the atom. Now, you want to see, and at that time, an American biologist were visiting Otto Frisch. And now, prior to that, I should backtrack that Niels Bohr had proposed the nucleus as a liquid drop model, so-called. So because of the so-called surface tension of the liquid water, a drop of water has occurred, the nucleus is like a drop of water, and it is split as to how it comes around and becomes like a dumbbell shape, and is split into two. And and it just kind of sort of looked like the two cells splitting inside under the microscope, as to how when the cells multiply. So Otto Frisch manages to ask his American biologist, what do you call when you split the cells? Oh, you call it fission. That's how the name fission came about. Okay, so that's the story as to how the word fission came into physics between there. So the word was actually borrowed from biology. And if you're familiar with UK, this is the fact that University of Birmingham, they showed the feasibility of an airborne atomic weapon. So and they calculated the various amount of uranium that would be required to produce energy and make a weapon of mass destruction. And this is one of his biographies. And again, he was an accomplished pianist. And so you can see that is the day when the word changed.
Sorry, Mr. Finch. I'm afraid it's too late. I think they found them.
So you can just reminded me of that is the way the word went mad, And the analogy of mad, you can see in the abbreviation that yes, it is mutually assured destruction. So when we discovered fission, it's about the time when we discovered so-called mutually assured destruction. And that became the post-war pop. Okay. Let's see what we can. Oh, sorry, I thought this was. And this is actually the timeline of fission. As we mentioned earlier, we have covered the Otto Hahn part and Frisch and Meitner. Now, Niels Bohr by that time was southern United States, and at Princeton, a conference of various physicists at the center in Princeton, and that's where we announced the results. And that's the first time America became aware of the properties of fission. And it will get more, and this was the amount of geometric progression that would take place. It's almost like putting rice grains on a chessboard as to how quickly it would multiply. And that's one of the ways chain reaction can be started. I see you have gone to the dark side. So that's when the word went to the dark side. And this is an interesting side clip.
Right away.
Okay, so this is, almost, you're almost on time, but I think we'll catch up next time. But I'll just continue for you, still have 5 minutes. So this was an idea that was proposed by no, I don't know that in 1934, but this was missed by the Curies. I mean, the younger Curies, Irene, and was missed by the great Enrico Fermi. And now this is interesting. Then when Otto Frisch and Lisa Meitner showed this paper to the great Niels Bohr, oh, he banged his hand on his head. Gee, how stupid of us not to think of it. Okay. And this gets even more interesting that later on, when Leo Szilard, who by that time had thought of chain reaction, he he had the concept that yes, this could be weaponized. But he was almost an unknown entity with a foreign accent in America. And he said, well, we need to make the government aware. Now, the biggest name at that time in America was Albert Einstein, who had made his home at the Institute of Advanced Studies. So he was persuaded to write a letter to President Roosevelt. Okay. Now, when Szilard, who did not drive, he went with Edward Teller, his friend, fellow Hungarian, to Einstein's home in New Jersey, and to write a letter. Serious, Einstein said, I didn't think about it either. So it just goes to show the famous ideas. And this was Einstein's letter as to, because of the danger that Hitler might first have the bomb, he signed the letter, which had been drafted by Leo Szilard and Eugene Wigner. And again, Einstein had some reservations afterwards. Had I known that the fear was not justified, I would not have participated in opening Pandora's box, because my distress was not limited to Germany. Okay, so he was skeptical about the whole this thing. But at the same time, they were all, German exiles, and that's one of the reasons why he put his famous name behind this letter. And this is the text of the letter that, again, so, and because he was a fast kid, so now it was difficult to get this letter because Roosevelt was obviously, so who would deliver the letter? The letter was delivered to him by a rich economist, industrialist friend named Alfred Sachs on October 11, 1939. Okay. And again, at that time, Roosevelt had enough things on his mind, that were going on, and including, rebuilding the post-Depression era. So again, he didn't think too much of it. So Alfred Sachs, he understood what could happen because he had enough interest in physics and background. So he understood. So he decided that he again went next day to visit Roosevelt. And he told him a story of, as well, during the French Napoleonic Wars, one American had an idea to build naval power based on steam. But Napoleon did not think much of it. And he just pushed him away. And so he told that if Napoleon had listened to this idea, the history of, what would have been different, okay, so he told the story again to Roosevelt, and that time says, okay, so do you mean, Alex, what you're after to see that the Nazis don't blow us up? Precisely. Okay, and that's when Roosevelt finally, I guess you can say that the light bulb went on, and he wrote this brief note, this requires action, FDR. And so they devoted a certain amount of funds to start research on uranium splitting and production. And at the same time, when Einstein heard about this chain reaction, Einstein's reaction was in German, pardon my German pronunciation, was daran habe ich gar nicht gedacht. I did not even think about that. So the fission reaction was so uncommon, and in terms of science, that a lot of the famous people did not think about it. But this was the start of the atomic project or research that was funded. Okay, and the main principles that were given was acquire uranium, because America did not have enough uranium at that time, while the Germans had the advantage of, because there were mines in Czechoslovakia, and so that they were able to acquire, and huge amount of uranium, and they were piling it up. And they were trying to buy it up from South America as well. Okay, and the biggest prize that had was from Belgian Congo. So the Americans tried to buy up a lot of the Belgian Congo production because Congo was under Belgian rule at that time. Okay, sorry. I think that was one. Okay. And at the same time, the Brits were also aware of it, type of thing. And the two physicists, who were in Britain, were working, they were ahead of this thing, and they had they formed a concept of a committee called Maud Committee. And a lot of time, now at the time, the Brits had the problem that a lot of these were Germans. So they, on one hand, they were enemy aliens, but they were still the smartest people around. And so the Maud Committee was military application of uranium detonation committee. And so this were some of the people who were involved in the concept. And so this was the start of the British effort by using, and so Otto Frisch, who we just mentioned earlier, and another scientist in Rudolf Perls, they formed the committee and calculated the amount of uranium that would be necessary to make weapon grade explosive device. And so by using so-called neutron reflector, they thought that they only need about 5 kilograms worth of pure uranium. Okay, sorry, 5 kilograms of pure weapons grade plutonium, or 15 kilograms of uranium to achieve what we call critical mass to sustain what is known as the chain reaction. Okay, and so this was part of the British effort headed by the scientist that we talked about, named James Chadwick, and along with various universities in UK. And the source was, the British Belgian Corps. Okay. And at that time, they were already losing some of the information to the Russians by the famous MI5 spies, the Russian spies, that we'll talk about it. We talked about spying later on. Okay, so I think we're coming up to now 12 o'clock, so we should stop at this stage. I'll stick around for a few minutes, and we are reasonably on time.